The data presented here are a series of historical oil prices, and these are measured over 65 days. And so we want to fit an autoregressive model of order 1 to this data. So an autoregressive model basically predicts the value of a future price based on the previous price. And so the previous price we'll refer to as the lag. And so the lag is simply the price from the previous period. So we'll start the series on August 12th, and the August 12th lag will be the August 11th price. And we'll copy that down. And so the idea of an autoregressive model is that there are some time series that are mean reverting. In other words, they revert over a long period of time to an overall mean. And so that's what we see here. And in this case, what we're going to do is fit a regression model to the prices, with price as the independent variable and the lag as the dependent variable. So the regression model looks a lot like this. Y is the price. We have a parameter beta 0, which is the intercept of the regression equation. We have a parameter beta 1, which is the slope of the regression equation. And then we have the lag. And there's an error term we'll just call A. And the error term in this case will be a white noise term. So we'll simulate that. So we need to fit this regression model. One way to do that is to use Excel. And so if we go to Insert, first of all, if you need to add in, if you go to your Data tab and you do not have the Data Analysis Toolkit, then you would go to File and Options and Add-ins. And down here under Manage Excel Add-ins and Go, you would check your Analysis Tool Pack and click OK. And then you should have the Data Analysis Tool Pack. All right, under the Data Analysis Tool Pack, we're going to use regression. Okay, so as we've noted here above, the Y range are going to be our prices. We have to start, we can only use the rows where we have both a price and a lag. And so we've got the price and the lag. And the way we've got this situated, there's not a label immediately above these, so we'll just leave the labels boxed unchecked. All right, and I'm going to just specify the output range out here. Okay, and so we'll click OK and get this regression result. All right, so here's our regression output. And the beta 0 parameter here is the intercept. And the beta 1 is the slope on the x variable. And so what we're going to do, I'm going to insert about 4 columns here. We're going to first calculate the fitted values, and then we'll calculate the residuals. The fitted values would be the predictions for the price based on the lag using the regression model. So we would use our slope, or intercept, excuse me, with absolute references, our slope times the lag. And so those are our fitted values. And this assumes that the average of the error term here is 0. So these are our fitted values. Now the residuals are the actual values minus the fitted. So we see some residuals are small and some of them are large, some of them are positive, some are negative. Now we'll calculate the mean and standard deviation of these residuals. So we see the mean is a really small number. Okay, very close to 0 if we change this to a number. We can see it's 0 to many decimal places. And that's good because that's an assumption of linear regression, is that the average of the residuals is 0. And so the standard deviation of the residuals is about 1.316. And we're going to use that when we do simulation to model the error term. Another assumption of linear regression is that the errors are normally distributed, and so we'll fit a normal distribution with these parameters and simulate the error term. So we're ready to do our simulation. And so we'll simulate this for, say, 5 more days. And what we'll do is our lag is in column D, so we'll extend the lag down to these new 5 days. Now we've got some zeros here, but that's of course because we need to fill in these values. Right here, we'll simulate our error terms right below the residuals. And so we need an at-risk distribution. And normal appears. You may need to find normal under your continuous distributions if it doesn't appear. We want the mean to be 0, and we want the standard deviation to be the standard deviation of the residuals. And I'll go ahead and put an absolute reference here in the definition box. You can also put it in the formula that appears in the cell. So we've got our error term assumptions. We'll copy that down. Okay. So now what we'll do, we're simulating this forward 5 days, and we will calculate the next observation as using the regression model with the intercept and slope, using the lag, and then using the error term. So it'll look like this. Intercept, slope, and then times the lag. I'll have to use my arrow because I can't see it there, but it's in D67. That's where the lag is on my sheet. And then we'll add in our error term, which we'll be simulating in at-risk. And so that continues our time series. Let's put that on a chart. I'll insert a line chart. And there we can see, we know that the last several values here are our forecast going forward. I'll move this out to the right. Now, one thing we want to do is we're going to be comparing potentially this autoregressive model to other models that we might fit, like an exponential smoothing model, okay, like an additive random walk model. And we need to have some ways to evaluate those, and we're going to use two error measurements. So I'm going to insert two more columns here. I'm going to calculate the squared error and the absolute percent error. And we'll do that for the actuals and the fitted values. And we can only do that as long as we have an actual data point, which is down to row 66 here, period 65. So the squared error is the actual minus the fitted value. The absolute percent error is the absolute value of the actual minus the fitted value divided by the actual. So it has an interpretation as a percentage. So we'll copy these things down. And again, I can only go this far. This is as far as I had true actuals. The other values over here are the new simulated values. In fact, we may want to, the idea would be that we would make one of these values an output, and we'll do our simulation in a minute. So what we would do is calculate the mean of the squared error. And that is an error term called mean squared error. And the absolute percent, so the average of the absolute percentages, is the mean absolute percent error. So it's about 1%. And we would use those if we have competing models to measure the error in this particular autoregressive model. In the assignment, for instance, you'll fit an autoregressive model of order 2 and fit the error. Now the last thing would be, I've got one output defined here. We could define multiple outputs, but now we can simulate the oil prices on these future days. And so here is our period 70 oil price. We have all the information on certainty intervals, on percentiles that we can use to make certain decisions.